This video is a topic regarding BOD. Now, let's define BOD. BOD is the biochemical oxygen demand, represents the amount of oxygen consumed by bacteria and other microorganisms while they decompose organic matter under aerobic. When we say aerobic conditions, this is a system wherein there is a huge presence of oxygen at a specific temperature. Now let's proceed with the formulas. The first formula is BOD5 is equal to the quantity of DOI minus DOF all over P. BOD5 stands for the amount of biochemical oxygen demand for the first 5 days. Now, the unit for BOD5 is milligrams per liter. DOI is the initial dissolved oxygen concentration. This is in milligrams per liter. And DOF is the final dissolved oxygen concentration in milligrams per liter. Now, P here is unitless. This is dilution factor. Okay. Usually, the formula for the dilution factor P is equal to the amount of wastewater sample all over the capacity of the BOD bottle. Usually, this is in 300 milliliters or 320 milliliters. It depends on the capacity of BOD bottle. But usually on my problem solving parts, I'm going to give the value of dilution factor P. Now, the second formula is L is equal to BOD5 all over 1 minus E raised to negative KT. Or if we're going to manipulate the whole formula, BOD is equal to L times the quantity of 1 minus E raised to negative KT. Now, let's define the following variables. L stands for the ultimate BOD. Okay. L here is the ultimate BOD. This is in terms of milligrams per liter as well. And K here is the deoxygenation rate constant. Usually, this is expressed as per day. And we have T here. This is the time duration of sample in days. Now we have the third formula here as BOD rem is equal to L minus BOD5. BOD rem stands for the remaining amounts of BOD, which is the difference between the ultimate BOD and BOD5. The fourth formula is the relationship of the oxygenation rate constants for different temperatures T and the K at 20 degrees Celsius. Now, KT is equal to K20 times, we have here theta, multiplied with, or theta is raised to T minus 20. Now, KD is the deoxygenation rate constant at any temperature in degrees Celsius. Now, the unit for KT here is per day. We have K20 here. This is the deoxygenation rate constant at 20 degrees Celsius. It is also per day. And we have the value of theta. Okay. Now, the value of theta varies depending on the given temperature of the sample. For temperatures greater than 20 degrees Celsius, you're going to use 1.056. Now, this is unitless. And we have the second value for theta. For temperatures ranging from 4 degrees Celsius to 20 degrees Celsius, you're going to use 1.135. Now, if we're going to plug in the values with T here, the temperature must be in degrees Celsius, not in Kelvin. I repeat, the temperature T here must be in degrees Celsius. All right, let's proceed with the mixing streams here. As you can see here, we have a first stream, second stream, and if both streams had mixed, we have a solution here. Now, this stream here, I'm going to label it as W. Now, we're going to consider two variables here. We have QW and LW, whereas the other stream as QR, LR, and the mixing or mixed stream solution here, okay, once these two streams had mixed, this is LA, and we have a variable of QA, but since we can add both QW and QR here, our QA now is equal to QW plus QR. Now let's define the variables. When we encounter these type of problems, these are usually mixing of streams of wastewater. So it's kind of gross. Okay, Q stands for the volumetric flow rate, cubic meters per second, and L is the ultimate BOD. This is in milligrams per liter. All right. Now let's solve for LA. Now this is the material balance, algebraic material balance for the whole mixing streams as QW times LW. LW here is the ultimate BOD at the W stream plus the volumetric flow rates in cubic meters per second for the R stream multiplied with the ultimate BOD LR in milligrams per liter, giving us LA times QA. If we're going to expand QA here, this gives us QW plus QR. Now, if we're going to solve for LA here, we need to manipulate the whole working equation by dividing it with QW plus QR. This gives us LA now, or the ultimate BOD for this mixed stream or solution. LA is equal to QW plus LW plus QR LR all over QW plus QR. Now, our next video is a first sample problem for BOD calculations.